Hello, welcome to our presentation. Today we will be showing off a flight debugger that we've been developing for Collins Aerospace. I'm Spencer Marcus, and our team consists of Andy Gabler, Nick Solem, Matt Vollen, and myself. Our project sponsor is Mike Vate, and he's been our point of contact at Collins for this project. I'll start with a brief outline of what we're going to be discussing today. I'm going to kick things off with an overview of Collins and the specific opportunity that our sponsor approached us with. Then I'll introduce our solution that we've delivered to Collins and the timeline that we followed to achieve this. After I finish outlining our delivered solution, Nick and Matt will be giving us a more in-depth look at the true user experience and the features of our product. To wrap things up, Andy will be going over some of the challenges that we faced along the way and giving a post-mortem on our project as a whole. First, we'll talk about what Collins Aerospace actually produces. Collins plays a part in producing all of the highlighted parts of the aircraft in this photo, and if you look closely, you can see that they cover almost everything from the safety slide in the back to the software that actually flies the plane. Our sponsor fits in right about there. His team is responsible for air-to-ground communications. While Collins did start as Collins Radio many years ago, today they have thousands of engineers providing solutions for commercial and military customers like Airbus and Bombardier. Recently, their parent company, United Technologies, merged with Raytheon to form Raytheon Technologies, and this will expand their reach in the aerospace industry even further. With that in mind, we can discuss the specific need that our sponsor came to us with back in January. As we said, his team is responsible for communications between aircraft and ground stations. Clearly, it is safety critical that aircraft always have a stable connection. Sometimes, though, there's still minor hiccups and things don't always go perfectly. For example, an aircraft may have connected to a ground station that was not physically closest during a flight. This was where our sponsor's team would step in and review aircraft log files to determine the cause of the problem and apply a fix to the underlying code that drives these communications. This previously required a large manual effort because engineers at Collins would have to dig through huge log files by hand to accomplish this. These can be hundreds of thousands of lines long or longer, and much of the information in them is not relevant to someone on our sponsor's team. So, this is not an efficient use of a skilled engineer's time. So, our sponsor came to us asking for a solution that would allow them to more easily locate areas in a flight that had problems with air-to-ground communications, ideally something a little more interactive. To solve this problem, we've delivered two pieces of software. The first deliverable is a local Python script that crunches the data from these aircraft log files and outputs the important parts that our sponsor cares about to a JSON file. This can be easily interpreted by other software. Our second application is a web page that takes in this JSON file and visualizes the data in Google Maps using its JavaScript API so that an engineer can inspect it in a much more efficient and interactive way. This web page also allows a user to play back a flight on the map so that a user can see how ground connections changed in real time as the aircraft was moving. We think this will be extremely helpful and cool for Collins to use. So, the expected workflow for an engineer with some log files they want to inspect would be to first feed the log files to our Python app for processing and conversion to a standard JSON format. Then they would open our web page and load in this JSON that they just generated. Now they can easily visualize and interact with the data, and we're very excited to show off the progress we've made in this area in just a few minutes. Before we give a demonstration of our software, I'd like to review the development schedule that we've used to get here. We used a series of 4 sprints, each around 3 weeks in length. In our first sprint, we got off to a great start, and our local Python application was feature complete by the end of this sprint. Of note is the fact that this sprint was the largest by estimated development effort, which definitely paid off as the semester wore on. In our second sprint, we made a first cut at our web application and learned about plotting data in Google Maps through its API. Our third sprint was focused almost entirely on developing the playback feature of our web page, with some slight scope additions in the Python application that allowed for a better user experience in the web app. This was another relatively large sprint, but it is important to note that 9 hours out of the 45 and a half taken to implement scope that was introduced in Sprint 3 were technically completed in Sprint 4. Our last sprint was focused mostly on improving the user experience and documentation of our software, as we were close to done with all of the features at its onset. This explains why our effort spent implementing and maintaining features was relatively low for Sprint 4, about half what it was for other sprints. The most interesting aspect of our development cycle was that we actually planned this really well, probably better than any of us expected. We're particularly satisfied given the state of the world over the last month or two. Despite this, good planning allowed us to still deliver what we feel is a quality product. Now I'd like to turn it over to Nick and Matt to demonstrate our delivered solution.
Hello. I will start off the demonstration by showing our Python application in action. Since one of the non-functional requirements of this project is a portable solution, we ended up creating a binary executable for our Python script to remove the need for the user to have Python installed. Using our application is as simple as running the executable. After the application is launched, the user is prompted for a location file using Windows built-in file picker. The file we are looking for is created by a service called FlightAware, which uses crowdsourced sensors as well as their own equipment inside of airports to log flight information being broadcast by an aircraft automatically. What we truly care about in this file, however, are the updates to the aircraft's location roughly every 15 seconds for the duration of the flight. Other information that is not needed for our project, such as the speed and altitude of the aircraft, is present in these files as well. This information is retained in the output in case it may become useful in the future for continued development by Collins. Next, the user is prompted for a log file. This is the file that is produced by the Collins equipment and contains the information regarding any radio connections that the aircraft has made. For development, we were provided with files that have had all proprietary information removed. Even with that information removed, for a relatively short domestic flight, we are still left with a 5.8 megabyte file that is more than 100,000 lines of text. Displayed now are the contents of this file. For the purposes of this application, we are only interested in the aircraft's active and inactive links, notated in this file by the inact and alink keywords. Any link that does not contain either of these keywords is removed. From the remaining lines, we retain information on whether or not the link is active, the hex code that corresponds to the ground station's name and location, and the E-value that represents the link's signal strength. After that, the user is prompted for a ground station lookup file. This file is a table that correlates a link's hex code to its radio type, location, and name. We created this file by hand in order to fulfill another development requirement of this project. It was expressed to us that this information periodically changes, so there needed to be a way to easily and quickly update it. With the CSV format, we were able to fulfill this requirement due to its simplicity and compatibility with more widely used tools such as Excel. Since the midterm, one of the more critical additions we have made to the log parser is greater tolerance for error. With this example, there are many ground stations referenced in the log file that were not present in the ground station lookup file we provided. Instead of proceeding silently without including any information on these ground stations, the user is notified of the issue and asked to make a decision. This is critical as the choice of whether or not to include these incomplete ground stations will have consequences on how the flight is represented in our web application. Additionally, there are extensive checks made within the log parser that ensure the user is aware where an issue happens if one does occur. This is important because we have not had the ability to test the application on more than a couple of flight logs provided by Collins, and want to ensure that our solution remains robust under any circumstance. Finally, the user is asked to choose a name and location for the output. If the file write continues successfully, any errors that were encountered while parsing are displayed. The output of the log parser is typically around half as many lines and only about 1/4 to 1/3 of the file size of the original logs, even when information that is irrelevant to our web application is retained. Here's an example of the output that is used to visualize and play back the flight in our web application. In addition to ensuring our solution was robust, we also spent time to make sure that our design was well documented. Shown here is the log parser's API, which lists and describes each method used within the log parser. We also provided a Python script that tested each piece of functionality in the log parser to give users a quick way to check that any changes made in the log parser would still be compatible with the web application. I'll now pass the demonstration off to Matt, who will show you the web application itself.
Thank you, Nick. Before I give a brief run-through of our finished web application, I would first like to give an update on the user story progress related to the web application since our midterm presentation. First off, I would like to say that the web application's associated user stories for all sprints are now complete. Our first user story is concerned with being able to see a Google map within a web page. This is now 100% complete as we have now received an API key from Collins. User stories 9 through 12 were 100% completed previously in Sprint 2 with no major issues. Previously, we hadn't got to thoroughly testing cross-browser compatibility. Since the midterm, we have now tested the application within Chrome, Firefox, Internet Explorer, and Microsoft Edge, all running with no issues. This makes user story 13 now complete. User stories 22 and user story 24 are both concerned with additional flight playback features, such as following the plane during playback and seeing a colored line from the airplane to each connected ground station. User story 22, following the plane during playback, is an example of a feature which we thought would be fairly easy to implement, but due to the instability this feature caused, as well as the limited time we had within our final sprint, Mike decided that this feature was not important to him and this user story was since removed. User story 24 was modified as it now displays the connection's opacity depending on the strength of the connection, as well as displaying as red if it's not connected to the nearest ground station and green if it is. The nearest ground station will also be circled green whenever there is a connection. The opacity of a connection from the aircraft to a ground station is dependent on its E-value, with a strong connection being more visible and a weak one appearing less visible. These additions seem simple at first, but required hours of reading Google Maps API documentation before they were properly implemented. This research was crucial to our development, however, as these features are now 100% complete. User story 25 is concerned with seeing which line of the log file corresponds with each time step location on the map. This was easily implemented by some short 1 to 2 line fixes within our Python script and JavaScript code. Each time step's location within the log file is now included within every time step info window on the map, which can also be seen here. And now I will briefly give a demo of our completed web application. First, I will select a JSON file outputted from the previous script Nick had just described. Since the midterm presentation, we have added the ability to play a flight in real time and watch the aircraft move across the map. The animated green circle along the flight path represents the aircraft. In this demo, you can also view any connections from the aircraft, such as this one here. This connection is green, which means it's currently connected to the closest ground station, and its E-value is 1, which means that the connection's opacity is changed accordingly. This connection is red, meaning it is not connected to the nearest ground station. Note that whenever there is a current link from the aircraft to a ground station, the closest ground station will always be circled green. In addition, we have implemented further playback controls, such as being able to fast forward, slow down, and pause a flight. Users can now select a portion of the flight they wish to view by dragging the slider accordingly. Numbers corresponding to each line within the log file have also been added to each info window of each time step. This is to make troubleshooting easier for an engineer at Collins. Finally, we have also added the nearest ground station indicator to the ground station layer, which can be toggled on or off with all ground stations. I will now pass it on to Andrew to give closing remarks.
Thanks, Matt. I'm going to talk about the risks, issues, and the team reflection now. As far as risk management goes, throughout the semester, we had tracked many of the different risks that we identified and updated them as they were taken care of to make sure that we were always constantly aware of what could happen. and also to have a documentation backlog so we were aware of what we had identified. So for the product in the future, now that we have no control over it, the things that we did to mitigate risk are things like putting in error checking for file types when uploading them to our log parser or onto the web app. We allow the users to select different options for what they want when creating the log file so that they can better debug it at a cost to the user. Then we have detailed descriptions that allow the errors that come up to be easier to figure out what's going on with them for the user so that there is no complete shutdown of productivity. So for those things, we have detailed documentation that we're going to be providing to Collins, and then we discuss the preferred outcomes with our mentor so that they could decide exactly what they want to happen with certain identified risks. And with that, everything should be managed well into the future as for what we had developed. For issues, there were obviously some bigger issues than normal this semester, mainly with the coronavirus impact. That was a completely unexpected out of the blue issue. I think our team handled it well. We managed to cope with the rapid change in the communication requirements as far as getting everything done on time and making sure we were all in communication, we were all working on the same thing. It's a little bit difficult to do that without seeing each other in person, but we were able to quickly get past that issue. Maybe 2 weeks of a little bit of miscommunication, but after that we had it all nailed down and everything was good to go. We had a little bit of trouble implementing the last minute user stories that our mentor had requested. He said that they were completely optional, like kind of stretch goals, so that wasn't a big issue as far as product finalization or anything like that. And then again, the team availability, due to the nature of our current situation, was a little bit different because we've got all these online classes now and people were moving and such, so the time requirements for online stuff was spread throughout all of our classes, not just this class. So we seem to have managed our issues well and got through everything. So here's our burn chart for the hours completed on our last 2 sprints. We started out a little bit slower, but we were able to catch up near the end because of the front loading that we had done earlier in the semester. We were more or less polishing up a final product, not implementing final product features that are required. Like, we had a solid framework to go before we started these sprints, so it was more of a polishing final sprint than it was a feature implementation one. Here's our effort breakdown. So we calculated this from our weekly reports, reading what we had said we'd done each week, which weekly reports helped that a lot. For the training, there were aspects of our team where one of us had a lot more knowledge than the other on a certain code base or something like that. So it was easier for one user to, instead of learn all that, just have one of us take over that and the other one can do documentation or something like that. Now for requirements, we spent a lot of time on those because this class loves to get us to document everything properly and make sure that we're ready for the real world with what teams want for documentation. So that was a quarter of our project right there. And then design and coding, those kind of went hand in hand. We couldn't really do anything coding-wise until we had the design down, so we spent a lot of time going back and forth on that and maybe changing some of the code based on new requirements requested for the design. And then testing, that was kind of our last end of sprint 4 that we worked on. And then for midterm and final reports, that'd be like this, and the midterm presentation, those took up a considerable amount of time, so that was about 15% of our effort. For reflection, I think our team handled well the change in communication due to coronavirus. We managed to pick up pretty quick. Front-loading the project helped out tremendously, especially with this unexpected curveball that nature gave us here. We were able to get right back on the ball and get on track. And our sponsor was very pleased with our final product. So I think it was nice to hear that. Our team is happy with what we created, and we're excited to see what they do with it.